Hello everyone, I am Nishad and I welcome you to our talk on improving intervention efficacy via concept realignment in concept bottleneck models. This is joint work with Myung, Karsten Roth and Zeynep Akata. Deep neural networks are known to be black box models that are hard to interpret. Some reasons for this include the large number of parameters, nonlinearities, and the high dimensionality of the inputs. For example, a crow might get incorrectly classified as a pigeon with no clear reason why. Concept bottleneck models make the decisions of neural networks more interpretable by grounding them in human interpretable concepts. They break down the classification process into two steps. First, they predict a set of human defined concepts in the image. Second, they use the predicted concepts to classify the image. For example, in this case, the model could think that the image contains a pigeon because it incorrectly predicted that the wings and upper body are gray. In addition to improving interpretability, CBMs also allow users to correct the output of the model by intervening on incorrect concepts. Here, by manually setting the colors of wings and upper body to be black, the model can correctly classify the image to a crow. However, human intervention is costly. In many cases, dozens of interventions might be required per image to correctly classify it, which is not practical. Our goal in this project is to improve classification accuracy with fewer human interventions. Prior works treat concepts independently. That is, intervening on one concept does not change the model's predictions of other concepts in the same image. Our main insight is that concepts in the real world are related to each other. Hence, telling the model that the wings are black can also likely hint that the upper body is black. In our example, there are two incorrect concepts, and it would take two manual interventions to correct them. However, if we can automatically update the predictions of all concepts after the first intervention, a single intervention is enough to correctly classify the image. Next, let's look at how we achieve this. In order to update the predictions of all concepts after intervention, we introduce a concept intervention realignment module. This module can be applied post hoc without changing the weights of the base CBM, making it lightweight and modular. Further, this module is agnostic to the intervention policy, making it flexible. The realignment module consists of two components. First, the concept selection policy, which decides which concept the user should intervene on. Second, the concept realignment model, which updates the values of all unintervened concepts. To train the realignment model, we keep the base model frozen and obtain concepts from the concept encoder of the base model. Then, we simulate the intervention process. For intervention step T, we select a concept using the intervention policy, then we intervene on it and feed the updated concepts to the realignment model. Then we compute the cross entropy loss between the updated concepts and the ground truth concepts and average the loss across all time steps. Now, let's look at some results. First, we show that realigning concepts after intervention improves concept predictions, leading to up to 70% reduction in the amount of interventions required to reach a target performance. We also find that improved concept predictions lead to better classification accuracies across all datasets. This highlights that our method reduces the amount of human effort required to reach a target performance. We also find that our method improves performance across multiple CBM architectures. Additionally, concept realignment can even be combined with the state-of-the-art approach of intervention-aware CEMs and further improve its performance. This can be done jointly or post hoc, showing the versatility of our approach. Finally, let's look at some qualitative samples. Here, we show an image of a crested auklet, which was misclassified as a parakeet auklet. We also show the 10 highest concept prediction errors. After one intervention, The image is still incorrectly classified, both with and without concept realignment. You can also see the concept prediction errors both with and without concept realignment. After 4 interventions, you can see that the concept predictions of many concepts have gone down. Now, the image is already correctly classified with concept realignment, while the base model still classifies it incorrectly. It takes 10 interventions for the base model to correctly classify it, and again, the concept errors are much lower with realignment. Thanks a lot. This was all for the presentation. Feel free to reach out in case of any questions and scan the QR code to read the paper.